So in the last video, we talked about one way to determine if a regression equation is useful, and that's through the coefficient of determination. In this one, we're going to look at another way, and this is through linear correlation. And linear correlation basically looks at the relationship between the two variables. And in this case, it's only two variables because we're doing simple linear regression with only two variables. The predictor variable, the response variable. So here we're looking at how well are those two variables correlated. And if they are strongly correlated, then we could say that our regression equation is indeed very useful. So again, this is just another way to look at the usefulness of our regression equation. It's a very common term in statistics, the linear correlation coefficient, which we're going to go over. And we hear the word correlation all the time, so through this example, we're going to look at, again, is the number of hours you study, how well is that correlated to what your test grade is going to be. So to do that, let's look at some graphs for a second to show different degrees of linear correlation. So unlike the coefficient of determination, correlation can be negative or positive. We can have a positive linear correlation, meaning as our x value increases, so does our y value. Or we could have a negative correlation. As our x value increases, our y value decreases. One thing to keep in mind when we're dealing with correlation, whether it's negative or positive, that is going to correspond directly to the slope of your regression equation. Because if you have a negative slope, you are going to have automatically a negative correlation. If you have a positive slope, you're going to have a positive correlation. So let's take a look at a few. The other thing we can determine is the degree of the correlation. So this first one in part A, we have what's called a perfect positive correlation. Our R value ends up being 1. So just like with the coefficient of determination, we will get a value, but now instead of it being between 0 and 1, our correlation coefficient, our correlation coefficient is going to be from -1 to 1, somewhere on this scale of -1 to 1, okay? If it is 1, as in A, or exactly -1, as in D, that's a perfect correlation, and it's perfect meaning every single piece, every single point, every piece of sample data fits perfectly on our regression line. Now, that often doesn't occur. So if we have, as indicated in B and E, where we have our values very tightly surrounding that regression equation, we would have what we call a strong. And that would be 0.9, maybe even anything above 0.7, I would say, or below -0.7. There is no kind of rule of thumb, but if you want to gauge whether something is strong, it's got to be at least above 0.7 or below -0.7. And then a moderate one or a weak one would be, moderate would be somewhere around our -0.5 or 0.5. And as you get down below 0.4, anything near 0 would be considered weak. So we have moderate around that 0.5 and greater than, some people, there is no exact number, but closer to 1, of course, and closer to -1 is strong. You can feel confident if you have anything at 0.8 or above to say it's definitely strong. Anything at 0, so to have a correlation coefficient of 0 take a look at G. That's where, again, we can't fit that linear equation. We kind of just look something like that. That means there's no correlation between our predictor variable and our response variable, our x and our y. Okay, so when you are doing, when you're calculating a correlation coefficient, again, you should be between -1 and 1. Whether it's negative or positive is directly related to whether your slope of your regression equation is negative or positive. And when you interpret it, you can use some identifiers such as strong, moderate, weak, negative, positive correlation. So we'll go through that in our example. But before we do that, let's kind of take a look at our formulas. And you'll see these formulas on your formula sheet. So here is our R. And let's go to our formula sheet for a second. So your formula sheet will list, this is our defining formula. But again, just like our other formulas, we have these computational values that we find that make just the rest of the works that much easier. And here we have R as S of xy divided by the square root of S of xx and S of yy, which will be the formula that you will use. Now, you may also notice, let's go back to the formula sheet for a second, that your coefficient determination is R squared and your linear correlation coefficient is R. And it is no coincidence that they both use an R. The other relationship between correlation coefficient and coefficient determination is the coefficient determination equals the square of the linear correlation coefficient. So you can find your coefficient of determination, which is R squared, by simply taking your correlation coefficient and squaring it. All right. What you need to be careful of is you cannot, and this is, we'll talk about this when we go through the example, but suppose I ask you to find R. If you simply do this, you will lose whether it is negative or positive. So we'll talk about that in a second. So you want to be careful just saying, oh, I'm just going to take the square root of R squared to find my correlation coefficient. But let's go through an example. So we're going to go back to our data again, where X represented the number of hours a student will study and Y was their test grade. We found all our values to help us calculate, and we had gotten a regression equation. We even, in the last video, found R squared, I believe, to be 0.60, so we'll put that up there as well. Now, what I'd like to do first to find our correlation coefficient is use our computing formula, which is the xxy over square root sxx sy. So go ahead and plug everything in. So that's going to be our negative 133.5 over the square root of 157.86 times 188, and I get just round to the hundredths, 0.77, negative 0.77. So here's where you need to be careful, because you might say, well, wait, I can just find, I don't know why I had the square there, I'm terribly sorry about that. I can just find R. Yeah, I accidentally put a squared on that one. Please take that off. I can find R by taking the square root of R squared, which is the square root of 0.60. That is going to give you, you can just check it real quick in your calculator. If you take the square root of 0.6, you will get the same value, except you are not going to get the negative. If you do it this way, you risk the chance of not knowing if it's negative or positive unless you take the time then to review your equation. Remember what I said, if you have a negative slope, you have to have a negative correlation. So we do get a correlation coefficient of negative 0.77. So we would interpret that as, so it's close to 0.8. If you want to call it strong, you can say it's fairly strong. I would say I would call this one fairly strong. I'd even go ahead and call it strong. We have a strong negative correlation between the number of hours a student studies and their test grade. Okay, don't get too caught up on, what you don't want to call that obviously is a weak. If you called it moderate, it'll be okay. I would probably say a fairly strong. Okay, there is no set standard. The closer to 1, the closer to -1, of course, is strong. Anyone surrounding 0.5 would be moderate, and then closer to 0 would definitely be weak. But I'm not going to set you up. If you call 0.7 strong instead of moderate, no big deal. But if it's a 0.6, you should say moderate, because that was definitely closer to 0.5. I would, if you want to do it this way, anything over 0.75 is closer to 1 than it is to 0.5, so we can go ahead and call that strong, however you want to do it. Okay.